We'll start maybe a minute or so after
Sounds good.
the hour begins.
Yeah.
All right. Hello, everyone. Welcome to the String Pheno online seminar series. Our first talk will be given by Hamza Ahmed at Northeastern University. And Hamza will be speaking about a twist on heterotic little string dualities. Hamza, take it away.
Thank you. Hello, everyone. So today first of all, I would like to thank the organizers for allowing me to speak here and keeping this nice seminar series going. So today I'll talk to you about some recent work that should be on the archive within the next few days, hopefully, with Paul Constantine-Ullman, who was a postdoc at Northeastern and now is at UCSB, and my advisor, Fabian Rula. So in particular, today I'll talk to you about the T-dualities of heterotic little string theories in the context of twisting. And of course, I'll explain what all this means as the talk goes on. So before we get into it, let me flash the outline for this talk. So first, I'll try to motivate why we are interested in little string theories and why maybe you might also find them interesting. Then I'll give a review of what these theories are, and in particular, what are the heterotic little string theories and what it means for them to be T-dual. And then we'll get into sort of the main goal of this work, which was to look at the landscape of twisted T-dual LSTs. And then using the techniques we developed there, we construct new twisted little string theories that, as far as we know, have not been constructed in the literature before. And then I will conclude. Okay, so why little string theories? So I guess what's most relevant for this audience is the fact that these theories are a subsector of every 60 supergravity theory with at least one tensor multiplet after we decouple the gravity multiplet. And in particular, the resulting theories are much more tractable than the full gravity theory because now they admit global symmetries, and in particular higher form global symmetries, which help us constrain the theory. And so in particular, I'll talk about the two group symmetries and the conventional flavor symmetries. I'll explain what two group means as later on in the talk. Furthermore, these theories still retain some of the gravity theory properties, such as non-locality, and what will be important for us, T-duality. And in particular, what I'll mean by T-duality is that I will take two 60 little string theories, put them on a circle, and get the same 5D theory. And so you can see sort of from this that these theories are a nice middle ground between gravity theories and quantum field theories. And in particular, one can, for example, use the T-duality properties to inform us about, say, the QFT properties, such as global symmetries, and vice versa, of course. And so in this context, two natural questions arise, is the first one of which is, what is the structure of this T-duality landscape or this T-duality map? And the second is, can we identify any invariants across any candidate T-dual theories that must match. And so in this work and in this talk, I'll sort of touch on both of these questions, but in the context where twists are allowed along the compactification circle. But before we get into that, let me sort of review what these theories are. So let's start from minimally supersymmetric 60 quantum field theories with at least one tensor multiplet. Then these theories have BPS strings in the spectrum, which couple naturally to the B field in the tensor multiplets. And one can associate to them a pairing matrix known as eta, and between these strings. And it turns out that the determinant of this matrix tells you what the UV completion of your 60 theory is. And so in 6D, the three supersymmetric UV completions we know of are the superconformal field theory, the little string theory, and the supergravity theory. And in particular, for the first two of these, the gravity multiplet is decoupled. And so again, sort of you can see how these little string theories are sort of form a nice middle ground between these two theories. And in particular, the fact that the determinant of the matrix for the little string theory is 0 will be important for us, as I'll show in the next slide, because this leads to a global symmetry in the theory. So as I said, these theories have tensor multiplets in the spectrum, and these multiplets have scalars to which you can give a vev. And once you give them a vev, you move on to what's known as the tensor branch of the theory without breaking supersymmetry. And on the tensor branch, this theory is just it can just be packaged as a quiver gauge theory. And so let me explain the notation for this quiver. So you have the gauge algebras here, labeled by G, and then you have the associated BPS strings, which are labeled by their self-Dirac pairing. So the diagonal of the intersection matrix. Furthermore, in accordance with the 60 anomaly cancellation conditions, you have bifundamental matter in the theory, and also some fundamental matter, which then leads to some flavor symmetry in the theory. Furthermore, there's certain massive matter in the spectrum. So this is all massless matter. So there's certain massive matter in the theory as well, which is not clear from the quiver, but it will be very important for us later on when we consider twisting the theory. So yeah, as I said, this matrix has a 0 eigenvalue, and this leads to a non-dynamical two-form field in the theory, which couples to the what we call then the little string. And it's easy to see why there must be such a field in the theory, because this eta matrix shows up as the coefficients of the kinetic terms of the scalars in the tensor multiplet. And so by supersymmetry, there must be an associated two-form field for which there's a 0 eigenvalue. And then its kinetic term also vanishes, which then leads to what is this non-dynamical two-form field in the spectrum, which then generates the U1 global one-form symmetry. And in particular, this linear combination that vanishes has the coefficients of it are what are known as the little string charges. All right, so now let's focus on heterotic LSTs. So these arise in heterotic string theory as the world volume theories of NS5 branes with some singularity G and some choice of flat connection for the E8 symmetry at infinity. So from the point of view of the world volume theory, this flat connection just tells you what the flavor symmetry of your heterotic LST is. And so in particular, so if you take a trivial flat connection, you just get the E8 times E8 flavor. And I'll label this theory by the symbol here. Furthermore, there is a nice realization of these theories in the Hojawa-Witten picture. So via heterotic M3 duality, with trivial flat connections, this looks something like this. So now these theories arise as the world volume theories of M5 branes, probing the same kind of singularity, and there are M2 branes that stretch between them, which then lead to the strings that I talked about earlier in the theory. And in the quiver notation that I introduced earlier, you can see sort of these E8 factors. These are the flavor symmetries, and then you have these gauge algebras G here, and there's some matter in between them, which can be perturbative or non-perturbative. One subtle point here is that this is what's known as the partial tensor branch of the theory. So the full tensor branch depends on what your singularity is. But the point is that on the full tensor branch, this curve configuration can change, and you can have other gauge algebras as well, which will the details won't be important for us, but we will see this later. Okay, so we have a similar story for the SO32 heterotic LST, but now we just have a flat connection for the SO32 symmetry at infinity. And furthermore, we have two kinds of SO32 heterotic LSTs. Again, this won't be very important for this talk, but just for completeness, these are what the one class is known as the theories without vector structure, and the other class is with vector structure. So let me sort of show you how these theories look like. So consider the case for the flat connection is trivial, and we have some general singularity G. In this case, the theory on the tensor branch takes the shape of the affine Dynkin diagram of the singularity, or its folded versions. And so let me show you this via an example. So consider the singularity E8. In this case, this is the quiver that you get. And in particular, note that the number of NS5 branes now is encoded in the rank of these gauge algebras. All right. So as I said, we want to look at the T-duality of these theories. So we would have to put these theories on a circle. So when we put them on a circle, we expect some 5D KK theory. However, sometimes if your theory has a discrete symmetry has a discrete symmetry, then you have the extra choice of turning on a discrete holonomy for the background gauge field associated to this discrete global symmetry. And in this case, you get disconnected 5D vacua, and each of those vacua is known as a twisted 5D theory. So the discrete symmetries we'll consider first are known as the auto-automorphism symmetries of the gauge and flavor algebras. So you can think of this as a generalization of charge conjugation that you have for a U1 gauge theory. And you can sort of also see these symmetries from the Dynkin diagram of the associated algebra. So here for E6, you see that it's a symmetry, it's a Z2 reflection symmetry of the Dynkin diagram. And in terms of the gauge fields, the statement is just that once you go along the circle, the gauge field is allowed to come back to itself up to an action of this discrete symmetry. And so for the gauge algebras that have non-trivial charge conjugation symmetries are given here. And in particular, note that the SO8 is special because it has a Z3 because of the triality. So one important point is that, as I showed you earlier, our LSTs have a bunch of gauge and flavor symmetries. And so naively, you might think that this theory has a charge conjugation associated to each of those algebras. However, that turns out not to be the case because we have massless and in particular massive matter in the spectrum, which must be respected by any candidate symmetry. So it would turn out that what always happens is that there is a diagonal of the full naive charge conjugation symmetry that survives, and this will be important for us later on when we twist by these symmetries. So now I can state what I mean by T-duality of these theories. So the T-duality of heterotic little strings just descends from the T-duality of the full heterotic string theory. And so let's take these two little strings, put them on a circle, potentially turn on some twist rho and rho tilde, and some Wilson lines. Let's encode that in these maps C here. And then the statement of T-duality essentially is the equivalence of these maps and the fact that you get the same 5D supersymmetric quantum field theory. And so indeed, one of the main goals of this work was to study the structure of this map when these rho and rho tilde are non-trivial, when you have non-trivial twists. And as we'll see later, this enriches this landscape of T-duality of heterotic LSTs. In particular, we get many more T-duals. All right. So as I alluded to in the beginning of the talk, we would like to have certain certain duality invariant data that we can identify on both sides as necessary conditions for T-duality. And so using field theory arguments, you can have these 4 pieces of data. And so the first line, so the Coulomb branch dimension and the dimension of the Wilson lines is essentially just a statement about the equivalence of the number of moduli of the 5D theory, which should, of course, match for any T-dual theory. And this is encoded in the rank of the flavor algebra and the total rank of the 5D gauge algebra. The second line is slightly more interesting. Here, these kappa R and kappa P essentially encode what is known as the 2-group symmetry of the theory, which encodes the mixing of the 1-form symmetry that I introduced earlier and the 0-form symmetry, so the conventional symmetries of the theory, the Poincare and the R symmetry in this case. And the reason, so the exact formulas are not important, but the reason we expect these to match is because these you can interpret these as certain mixed anomalies in the theory. And of course, for any duality, we expect the anomalies to match. And so indeed, one of the main goals of this work was to show that when we allow for twists, so this N here tells you the order of the twist. If we allow for twist, does this data continue to match for T-dual theories? And in all our examples in the paper, we showed that this is indeed the case. Furthermore, which is another interesting point, is that kappa P is always known to be 2 for heterotic LSTs, the ones we'll consider in this paper, and kappa P is 0 for type 2 LSTs, which I haven't talked about, but these are the other kind of LSTs. And so the interpretation that's given to this is that it counts the number of M9 branes in the theory. So this makes sense. But then a natural question arises, are there heterotic LSTs for which kappa P equals 1, i.e. there's a single M9 brane? And so by the end of this talk, hopefully I'll convince you that such theories do exist. And finally, as I said, this data is sort of the necessary data that you need for T-duality. So so the way to prove the duality would be to construct these theories via their F-theory realizations, via F-theory on a Calabi-Yau threefold, a genus-one fibered Calabi-Yau threefold, and then use MF-theory duality to prove this duality. I won't talk about the geometry much in this paper due to the lack of time, but in our paper, and indeed one of the novelties of our work was to have explicit toric realizations of all these duality chains that I'll tell you about, and prove the duality in that way as well. But in this talk, I'll just stick to the field theory, and if you have any questions about the geometry, I'm of course happy to answer them after the talk. All right, so let's now get into how we were able to chart this twisted T-duality landscape. So our main strategy was to use the invariant data that I just showed you as our guide to find these theories. So let's start from just any heterotic LST with some singularity G and some number of 5 branes. So call this theory K. And so in this case, you can show that the Coulomb branch and the kappa R both go linearly in M, which is the number of 5 branes. And these coefficients C2 and R2 are actually fixed by the singularity type. And then the C1 and R1 are essentially fixed by the flavor symmetry. So one strategy to find duals in families of M would be to match this leading piece across duals, and then try to find if there's a flavor symmetry or a flat connection that also matches this constant shift. And so indeed, this is the strategy we used. And so this tells you a necessary condition for T-duality, which is essentially that if I take a theory with some coefficient C2 R2 and some other theory with coefficient C2 tilde R2 tilde, then the hope would be that you can match the leading M term by compensating with the number of 5 branes. So C2 and R2 are known for untwisted theories. And we can actually determine these very easily for twisted theories via some field theory analysis, which is what we did in the paper, taking into account the massive spectrum and so on. And one thing which we find, which is interesting, is that kappa R and kappa P, so the 2 group structure constants, are not modified under out-automorphism twists. So really what we need to care about is the Coulomb branch coefficient that changes under twisting. So indeed, this is a strategy we use. And one immediate consequence of this is the fact that the consequence of matching this leading M piece is that we can now, this predicts the duality between an untwisted E8 times E8 heterotic LST and a twisted E8 times E8 heterotic LST. And so for the pairs of algebras for which this happens are given here, as long as the number of 5 branes are related via are related to the order of the twisting in this way. And so this is a very interesting result because we don't know if there's a group theory reason for these algebras to be paired in this way, but the physics seems to tell that there is something there. So regardless, we have this, we can just write down this duality chain where the first two are the E8 theories I just mentioned. One of them is twisted, one of them is untwisted. And then using just regular T-duality, you expect some SO32 duals as well. And in this case, you will find 2 of them corresponding to the plus and the minus. And so indeed, in our paper, we show that beyond just the matching of the leading M piece, we can also match the constant pieces by choosing an appropriate flat connection every time. And so indeed, these theories are fully T-dual beyond just the matching of the leading M piece. And furthermore, we also provide explicit geometries that again give further evidence for the conjectured for the duality between these theories. So let me illustrate this via an explicit example. So consider some number of 5 branes probing an E6 singularity. And so this is the full theory on the tensor branch. And naively now you may expect that this theory has a charge conjugation associated to each of the E6s and the SU3s in this chain. However, as I mentioned earlier, the massive spectrum has a role to play here. And so in particular, in this case, the massive spectrum comes in the form of this E string. And it basically imposes the fact that there's only a diagonal Z2 that survives. And that's the true discrete symmetry of the theory. And then we can twist by this single Z2, and we get the following 5D theory. And also notice that the U1 flavor symmetries are gone. So these U1s are gone because again, the massive spectrum imposes that you must project onto charged singlets under the U1 in 5D. And then from the table that I showed earlier, you expect an E8 times E8 theory that's dual to this theory with an E7 singularity. And so we can actually write this down explicitly, this theory down explicitly. This is the full theory. And this is dual to the one from the previous page when the number of 5 branes are related in this way. And indeed, we also proved this duality further via explicit geometries. And another interesting thing that we found was that you have 2 different families of duals, depending on if this n, which is the number of 5 branes of the twisted theory, is even or odd. And furthermore, if I showed you the Z3 example, so where you had a Z3 twist, then we find 3 different families of duals. So it seems like this order of the twist is playing a deeper role than we so far understand. And of course, it'd be good to understand it. Finally, let me also flash the untwisted SO32 duals to complete the duality chain that I showed earlier. These duals are given here, and in our paper, we also have examples where the SO32 duals are also twisted, and we explain why sometimes that happens and other times it doesn't. All right, so so far we've only considered discrete symmetries which we twist by that are charge conjugations. However, these theories on the tensor branch, well, any 6D theory with a tensor branch can admit other symmetries, and in particular these symmetries that are the permutations of tensor multiplets. And so one can think about twisting by these symmetries. And when one does that, the new feature compared to the charge conjugation twist is that now this eta matrix, so the Dirac pairing matrix, can also change in 5D. And in particular, now these indices alpha and beta in 5D label the distinct orbits of this symmetry action. And an immediate consequence of this fact is that the two group structure constants can now be modified, because if you write them down, they have explicit dependence on eta and on the little string charge, which obviously comes from eta. And so using this fact, we constructed what we call CHL-like twisted LSTs. So let me illustrate this via an example. So you take two M5 branes probing an E6 singularity. This is the fold theory that you get on the tensor branch. So you see these E8 factors here. Now you see that this theory has a Z2 permutation symmetry about this 3 curve. And so you can then twist by this symmetry. And when you do that and you compute the relevant data, you find that kappa P is 1, which is what I promised you earlier, the fact that now we have a theory which has effectively a single M9 brane in 5D. And sort of you can see this from the fact that we are identifying these E8 factors. And so we are identifying the M9 branes. Furthermore, we were also able to find SO32 T-duals to these new kinds of LSTs. And again, these arise for some sort of tensor twist of this theory right here about, you can see that now it's symmetric about the this 1-4 curve combination. And so we can twist by this. And again, once you do that and you compute the relevant data, you find that the full T-duality data matches. And so at least based on the matching data, these two theories are dual. And we also, in our paper, we have this, we have a table where we list all these possible kappa P equals 1 type T-duals. So what's important, however, is that we don't have geometric constructions for these. So this is essentially using this higher form symmetry structure of these theories to predict T-duals with kappa P equals 1. All right, so now let me just conclude. So the main goal of this work was to extend the T-duality landscape of heterotic LSTs by including these twisted little string theories by explicitly matching this higher form symmetry data and the moduli. Even though I didn't talk about this much in the talk, we provided explicit geometric constructions that proved the duality chains that we predicted via field theory. And finally, we provided field theory evidence for the existence of novel little string theories with kappa P equals 1. And so, of course, now you can think about doing a lot of things, and I'll mention a few of them here. So in particular, we would like to have geometric constructions to prove these theories are actually dual, the kappa P equals 1. Also, the geometric toolkit that we have for LSTs can be easily applied to SCFTs, and in particular, higher rank twisted SCFTs. So that would also be something that would be interesting. And then finally, it would be nice to have sort of a link with the 6D supergravity theory, in the sense that, as I said, that these theories form a subsector of the 6D supergravity theory. So how does this twisted T-duality embed into that story? And finally, I'll just flash a slide with this chart from our paper, which basically shows one corner of this T-duality landscape with these various twists relating to theories. Thank you.
Thank you, Hamza, for the very nice talk. Do we have any questions from the audience? Florent raised a hand. Please unmute yourself.
Yeah, hi, nice talk. I just have a question about the T-dual invariants. Upon twisting, do they change by something predictable, like shifted by the order of the twist or something like this?
So for the auto-automorphism twist, for example, only the Coulomb branch changes. So when you twist an algebra, you know what its resulting Coulomb branch is. So the twisted algebra, you basically identify some roots of the Dynkin diagram, and so you know what the Coulomb branch is in that case. for the case of the base twist, yeah, there is something that we can use to predict if the two group structure, when the two group structure constants change. So for example, if you look at the, if you look at the partial tensor branch, if your twist on the partial tensor branch is about a fixed node, then the two group structure constants actually do not change. So the example that I showed you here, the two group structure constants changed because the partial tensor branch actually does not have a fixed node. So when you twist, that leads to a change in the two group structure constants. But I'm not sure if that's the kind of predictive power you wanted, but.
Okay, so a priori, if I give you a mysterious LST, you can't directly predict what the new T-dual invariants will be.
Yeah, I mean, I think I can, because I know how. I guess I think I can, because I know what the rank of the twisted algebras will be.
Okay, yeah, okay, fine. Yeah, thanks.
Do we have any other questions for Hamza?
All right. If not, then maybe we can thank Hamza once again. And George,